The energy diagram is, it can look like a special topic in the study of energy, but it is really an enormously powerful way to look at how a system is going to behave if you know about its potential energy. So let me make a picture here of what's going on. So let's make a diagram of the potential energy of a system as a function of say, the separation of two objects that are in the system. And for gravity, I know exactly what that is. For a spring, I know exactly what that is. But let me just draw, some strange thing which maybe can come out of the study of some chemical reaction. So there's what the potential energy is. It's got its smallest minimum here. It's got a metastable state here. It's unstable right there. So that's what the energy of the system is. Now, if this is an isolated system, we know that the kinetic energy of the system plus the potential energy of the system, its change is equal to 0. That is the work from the surroundings. So I know that no matter what goes on, the kinetic energy of the object plus its potential energy is equal to some constant, which I'm going to call E0. That's the mechanical energy of the system. And the mechanical energy is something that I get to determine from my initial conditions. I could say I want the objects to move really, really fast. That puts a lot of energy in the system. Or I can say they're at rest. That puts less energy in the system. No matter what, this E0 will not change until there's some interaction with the system. So let me pick some E0. There's E0. So I got these two energies which are being compared. The total energy of the system, which is this blue dashed line, and just the part of the system energy that's the potential energy. So if I change the E0, I'm going to change the behavior of the system. So, however the system behaves, I need the total energy of the system to still be E0, but I need its potential energy to be following this black curve. That means that there are some regions in space that the system just cannot have. If I want the system to have this R here, if I go all the way out here, that is the value of the potential energy that I need to have. That's what this curve says. The total system energy is still the blue line, so in order for my kinetic plus potential energy to be the total energy, I need my kinetic energy to be less than 0, and that can never happen. Potential energy is never less than 0. The least you can get is when the kinetic energy is exactly 0. If the kinetic energy is exactly 0, I have all the energy in the system is just the potential energy, and that happens at these two spots. That's the only spot where the potential energy matches the total system energy, and that's where the system has to stop. There's no kinetic energy there. So if I can watch what an object does when the object, so let's suppose I release an object from rest right here. Well, it starts at rest, it's got a lot of potential energy, but the very first thing that's going to happen to it is it's going to be interacted with by this potential energy. It's going to move inward to here, and now it's got some delta K, which is greater than 0. Now it's going faster, and it's got less potential energy. It will speed up to this spot, and then it will slow down again until this spot, and then it will start speeding up again. It will be moving its fastest right there, and it will come to a stop right there. So it will, that's called a turning point. And it will just go back to this other turning point, and it has to stop there because once it gets to here, its kinetic energy is equal to 0, which means V is equal to 0. And if V is equal to 0, the force will drag it back in. So here is a bound state. The object is going to go back and forth between these two extremes forever. Let me change now to a different energy, E0, here. Now, depending on what initial position, the initial R you pick, and the initial, depending on what the initial R is, now let's suppose I pick my initial state in here. I can go out to this turning point, and then I come back in. I've got this, I'm trapped. I'm trapped in this, that end of the system. I'm always going to oscillate between this turning point and that turning point. I can, even though I've got the correct energy, I never get out here. That's a classically forbidden region because you have to go through this spot here where your kinetic energy is less than 0, which does not happen. So, sometimes a very useful thing to do when you make one of these energy diagrams is to shade the region below the potential energy curve because you can never get to there. whatever energy you pick, as long as you can be in the unshaded region, as soon as you get to a shaded region, you have to stop and turn around. So there's a couple implications here. Let's look at what this looks like for a spring. What this energy diagram looks like for a spring. So a spring, the potential energy for a spring is a quadratic. U is equal to 1/2 k x squared. So there's the x direction, there's the potential energy, U. And you know what this motion is. This is going to be this oscillatory motion. It goes back and forth with a set amplitude. Oops, let's undo that. It'll go back and forth with a set amplitude. There's the amplitude of the motion. And it has a period, which is related to the k and the mass. No matter what you pick for the spring, you're always going to have bound orbits. So you can never get to this red shaded region. You're always going to have some amplitude, whatever energy you pick. For the gravity interaction, sometimes you've got bound states, sometimes you don't. So let's look at what the gravity interaction looks like. This is the universal gravitational interaction. So here's the region you cannot get to. And now, if I pick an energy here, if I start here, I will go out to some spot, I will stop, and turn around and fall back to the Earth. So this is the highest spot you get to. If I choose a little bit more, so let's say that there is the surface of the Earth. So I'm always going to start at the surface of the Earth. If I start at the surface of the Earth with more kinetic energy, I can get to a higher spot. So this is more K, I get to a bigger R, until I get to a particular energy where I never actually touch the curve. That is this amount of kinetic energy. If K is equal to G M M divided by R, then I will never stop. And that K, you only get that K by getting some velocity. The corresponding velocity is called the escape velocity. It doesn't mean that gravity is zero out far away from the Earth. It just means that gravity is not strong enough to bring you to a halt and bring you back to the Earth. So if you throw something, what comes up, what goes up, if V is less than V escape, must come down. Doesn't have to, though. If I pick an energy out here, not only do I wind up going forever, my energy, my kinetic energy, is going to approach some constant. So my velocity is going to approach some V, which is not zero. I'm not going to approach some asymptotic rest state. I'm going to have some kinetic energy even when I am infinitely far away from the Earth. So these energies bound. This one's the borderline one, and these ones are unbound.